Okay, greetings AP Chemistry, this is Mr. Harper, and today what I'm going to talk to you guys about briefly is a brief word on spectroscopy. I'm going to explain the point of some of what you guys did in the lab and kind of like the ideas behind it very briefly. I'm going to introduce to you guys an equation called Beer's Law, or the Beer-Lambert Law, and I'm going to give you guys some supplemental problems to do with that. It is one of those kind of like outside topics that occasionally appears in the AP exam, and so you guys want to understand that. And for those of you guys who were not here in class on Friday, I'm going to describe to you guys briefly how to do the calculations for the lab. Now, be advised that if you were in third period, you need to call your group members this weekend and find out whether or not your data is any good, because we unfortunately discovered while we were analyzing the data that about half the class's data was not very good because one of the spectrophotometers did not work properly during the experiment. So please do call your group members and find out if you were one of those people, and if you were, then get the new data from your group. Okay, so let's talk about what this spectroscopy thing is. You guys might remember we used something called a spectrophotometer in the lab the other day. What that really says here, spectro kind of refers to the spectrum. We can select a wavelength of light that the device is going to emit, and then a photometer is something that measures the amount of light that we're bombarding something with. So here's the basic idea, okay? You guys had a cuvette, okay, which was filled with a solution. You bombarded this baby with some light, okay? Now, we were able to control with the instrument the wavelength of light that we bombarded the sample with, what part of the spectrum it came from. That was 445 nanometer light, or it was in the blue part of the visible spectrum. What the device does is it measures how much light it's using to bombard your sample with, and it measures how much light passes through the solution right there, okay? The amount of light that passes through the solution is called transmittance, okay? And what the device read out, there were two things you guys saw. It gave you a percent transmittance, basically the percent of the light that was bombarded, that was used to bombard the sample, the percent that came through. And then you also had also listed something called absorbance. The shorthand for absorbance, by the way, guys, is usually A or sometimes ABS, like that, okay? Now, there is a relationship between these two things, absorbance and percent transmittance. Absorbance is a scale that measures the amount of light that got absorbed by the solution, okay? Here is the relationship. Absorbance is equal to negative log of the percent transmittance, okay? So this is how we can convert between the two right there. Now, the reason I had you guys measure both in the lab and why the directions call for it, where I have to measure percent transmittance and absorbance, because both scales are given on the device, is that if you have either very small concentrations of the dissolved stuff, which is going to lead to a low absorbance, or very high concentrations of the stuff, which is going to give you a very high absorbance, it actually is a more accurate thing to do to measure the transmittance instead, and then calculate the absorbance with that information. So that's why you guys recorded both scales. However, during the experiment, during the analysis of your data, you are only going to use your absorbance values. The data looks good enough to where I don't have to actually have you guys do this conversion. You guys are going to use your absorbance and the standard curve that I provide for you to do your calculations later on. I'll talk about that a little bit later. Just kind of be aware of the connection between these two things. Transmittance and absorbance are kind of like inverses of each other, sort of, kind of, except this is logarithmic. So, okay, let's talk briefly about what spectroscopy is and what the point is, okay? The basic idea behind spectroscopy is this. What it is it's the study of electromagnetic radiation, which is always known as light, that is either emitted or absorbed by by different chemical species, okay? Spectroscopy, there's different kinds of spectroscopy. You can do ultraviolet visible spectroscopy, which is what we were doing the other day, where we look at the amount of visible light or ultraviolet light that gets absorbed by something in solution. You can do infrared spectroscopy, which measures the amount of infrared light something absorbs, what have you. There's different kinds of spectroscopy dealing with different parts of the spectrum, okay? But that's what spectroscopy is we're looking at how much light is basically either emitted or absorbed by something. And we might do that for different reasons. Something we know is that different chemicals will absorb different wavelengths of light in different amounts. And usually the amount of light that something absorbs, or the wavelength of light that it absorbs, can tell us something important about what that chemical is or how much of it is present, okay? We can use this to measure how much of a chemical is present, or in other words, to determine, we can find from this the concentration, okay, by measuring the amount of light that something absorbs, because what we saw the other day is that the absorbance of something is proportional to the concentration, okay, that species dissolved in solution. So if we look at how much light the thing absorbs, we can figure out from that how much of it is present. And the other thing that we use spectroscopy for is to identify something. If we have something and we don't know what it is, like say I have some organic chemical and I don't know what kind of organic chemical it is it an alcohol, is it an acid, is it an amine, is it a ketone, what have you? Okay, a very common thing that you will do in organic chemistry when you guys get to college is infrared spectroscopy. You'll look at the wavelengths of light that are present, and that'll give you a clue as to what that organic thingy is. Specifically, what functional groups are present in the molecule. Maybe later, and by the way, guys, functional groups you might remember are things like if we look at an alcohol, they all have an OH group. If you look at an acid, they all have something like this, a C double bond to an oxygen and an OH like that. And amines all have NH2 groups, things of that nature. Okay, that's what I mean by functional groups. So we may actually do that later in the year where I give you some unknown organic chemicals and I have you determine the functional groups from an infrared spectrum or something like that. I'll show you guys how to do that later. But I just want you guys to understand what we use spectroscopy for, to figure out, generally speaking, either how much of something is there or to identify what something is. And this is something that, so far what we've done during the year, guys, are classical techniques. We've been determining molar masses and things like that and looking at freezing point depression and other observable characteristics like that. Well, when you guys go to college and you start doing modern, well, it's not that what we've been doing isn't modern, but this is like something that if you were working in a lab, you do spectroscopy all the time. And also mass spectrometry, which we may look at later in the year too. So, all right. Now, what you did in the lab, we already talked about, kind of at the beginning. Okay, so you zapped your cuvette here with some lights, okay, in the machine, and you measured the absorbance that had that little scale thing. Okay, so you had, on the top, you had transmittance, on the bottom, you had absorbance, and you measured how much light got absorbed by that thingy in the lab, okay? Now, what we can do with that is we're going to use this information to figure out the concentration of your complex ion that is present in the solutions, okay? That is the entire purpose of using the spectrophotometer. You're going to find the molar concentration of this guy once your solution has reached equilibrium. And there's more than one way that we could do that. In this lab, we're using something called a standard curve, which I'm going to describe to you guys secondly, okay? But like we already said, there is a relationship between the absorbance and the molar concentration. These two things are connected. And they're actually connected by a very simple algebraic equation, which you are not using for the lab, but you might need to know for later on. This is called the Beer-Lambert Law, or sometimes also just called Beer's Law. This is something you guys need to take notes on and remember. Okay, it looks like this. A is equal to epsilon times L times C, or sometimes it's just called A is equal to A times B times C, where the A here, in either case, is the absorbance of the solution measured using a spectrophotometer, okay? L, or B in the equation, depending on which statement, it's written in different ways, different places, just again, because chemists like to confuse you, okay? The L here is the path length, okay? Really what that is how far the light is traveling through the solution. So if we're looking at at a standard cuvette, this could be something like 1 centimeter, for example. That's the diameter of the cuvette, how far the light travels through the solution. The the greater the path length, the farther the light has to travel through the solution, the more it generally is going to get absorbed. And so that's why that matters here in the equation. And then the C thing right here is the concentration of the solution, and this is usually measured in molarity, okay? Now, the last thing here we have not defined is this guy, epsilon or A. This has two names that are sometimes used. It's either called the molar absorptivity coefficient, or sometimes called the molar extinction coefficient, okay? And what this term describes, it's different, okay? Something you guys want to write down about this value is that it is different for all different chemicals, okay? And it depends on the wavelength. What this tells you for a given substance is basically how strongly it absorbs light at a given wavelength, okay? Now, you guys already know, kind of instinctively, that different chemicals will absorb different wavelengths of light. Like, for example, I like to wear blue shirts. When you see me wearing a blue shirt, what you are actually seeing is the blue light that is reflected by my shirt, and the shirt's absorbing everything else, okay? What this and so basically it might be my shirts might be reflecting a wavelength of light that's like at 445 nanometers approximately or something like that. Okay. Now, if you were looking at the chemical dyes that are in my shirt, what the molar absorptivity coefficient would tell you for that substance is how strongly it absorbs different wavelengths of light. Okay, if that makes sense. Now, you're not going to have a test specifically on this or anything like that, so don't worry too hard about it. It's kind of a minor topic, but you may have a question on my test that deals with Beer's Law, so I'm going to have you guys do a few problems just so you're familiar with it. It is super duper easy. We're going to do one example here on the podcast, okay? So here's an example. And I'm going to show you guys here how really this is the utility of the equation, okay? Suppose we have a pink solution containing an unknown concentration of cobalt ions. You guys remember we had that cobalt solution in class the other day that had the pink color. So say we have that solution and we have an unknown concentration of these cobalt 2+ ions. We have the absorbance that's been measured and it's 0.60. Notice, guys, this is a unitless number. The reason why it is unitless is because absorbance is a logarithmic scale, and so it doesn't have any units once you take the log of something. It's just kind of by convention. pH, as you guys are going to see in the next chapter, is kind of the same way. Okay? So the absorbance is actually be 0.60 at a wavelength where epsilon equals this right here. Now, it doesn't tell you what the wavelength is, okay? The wavelength doesn't matter to the calculation, but the point of saying this here is that this value of epsilon, the molar absorptivity coefficient, depends on the wavelength. It'll be different at different wavelengths, or if you want to think about it this way, it'll be different for different colors of light. Okay, so the unit, or the magnitude is 12, and the unit is liter over mole times centimeter to the -1 power. So that would look like this, 12 liters over mole times centimeter, okay? Where this centimeter thing here is dealing with the path length, basically, okay? It says the width of the cuvette is 1 centimeter. What is the concentration of the cobalt ion, okay? So how you would use Beer's Law here? We're going to write it down first. Absorbance is equal to the molar absorptivity coefficient times the path length times the concentration. I want to find the concentration. Now, if I had these other data, I could solve for anything, okay? But here we want to find the concentration, so I'm going to need concentration by itself. Concentration is equal to the absorbance divided by the molar absorptivity coefficient times the path length of the cuvette. Okay? Okay. So notice in order to find the concentration, I have to know these three things. I have to know the absorbance, I have to know the molar absorptivity coefficient, I have to know the path length. I know these things, so I'm just going to plug them in. The absorbance here is going to be 0.60 divided by the molar absorptivity coefficient is 12 liters over mole times centimeter. And the path length here is 1.0 centimeter. Now, when I look at my units, the centimeters is going to cancel out, okay? Now, these units here are in the denominator of moles is in the denominator of a fraction that is under the fraction, so that's going to flip up top in the calculation. So, once I go through and I figure it out, I'm going to get a unit of moles over liter, which tells me concentration. If I take out my calculator here, guys, and I divide this stuff here, so 0.6 divided by 12, okay, actually, we don't need a calculator for that. What am I talking about? It's going to be 0.050 moles per liter, and there we go. So we just use this easy relationship here to figure out the concentration of an unknown solution. But in order to do that, I had to know the molar absorptivity coefficient. I had to know the path length of the cuvette, which I can get from measurement, and this I have to figure out by an experiment. Okay. Now, so you're gonna do some problems practicing using this formula here for homework over the weekend. Now, you're going to ask me, well, Mr. Harper, this looks really super duper easy. Why do we have to go through all this work, and why do we not do that in the lab? Okay. The reason why we're not using the simple statement here of Beer's Law is because if we're talking about things over a range of different concentrations, it's actually much more exact to use something called a standard curve, okay? If I'm using Beer's Law, what this is assuming, the underlying assumption is that if I'm using this for different concentrations, we're assuming that the absorbance range of my instrument performs well over the entire range of absorbances, and that's not often true. Oftentimes, a spectrophotometer will not have a linear performance range. And what I mean by that is that it will measure the middle concentrations, kind of like mid-range concentrations. It'll measure the absorbance very well, but at low concentrations and at high concentrations, the absorbance becomes pretty inexact. Okay, so it's better to use a standard curve like this. Now, what a standard curve tells us, if you were in class, you'll know this, is here on my y-axis, I have the absorbance. Here on the x-axis, I'm going to have the concentration of the thing that I'm trying to find. In the lab that we did, guys, this concentration is going to be of the complex ion, because that's the entire point. We're using spectroscopy to figure out the concentration of my complex ion, which is FeSCN2+, okay? Now, I made the standard curve, and what I did is I prepared solutions. If you read the front part of the lab, it gives you directions for making standard solutions. And the point of these standard solutions is that because I have this ginormous excess of iron ions, it basically is going to force the production of the complex ion. All the thiocyanate that we usually have in those solutions gets converted into this complex ion. So I know that once I mix those chemicals, I know what the concentration of the complex ion in those solutions is going to be. I put those known concentrations down here on the x-axis, okay? And then for these different solutions, I measured the absorbance. So what this is going to tell me is I know then the relationship between the absorbance of the solution and the concentration of the complex ion for that set of solutions. And this is, again, at a specific wavelength. We measured this at 445 nanometers, okay? So what I did then is I made a graph, and you can see there's a linear relationship, and I got a regression line where I set, if we kind of extrapolate this back, I couldn't make it do this on the newer version of Excel. It kind of made me mad. I don't remember how. But if you extrapolate this back, you're going to see here that the y-intercept equals 0. And the reason for that is, guys, that if we're saying the complex ion is what absorbs light at 445 nanometers, at 0 concentration, we ought to have 0 absorbance. And there we go. So saying that forcing the y-intercept to be 0, here is my regression line equation that I got for my standard solutions, okay? Y is equal to 4196.5x, okay? Now, in this equation, the y value is the absorbance, and the x value, and what x represents, is the concentration of FeSCN2+ in the solution. So how you're going to use this, okay, this is a relationship that I found out from things that I knew. Well, here's the thing. If you have a solution where you don't know the concentration of the complex ion, but you've measured the absorbance, I can use this equation to figure out the concentration of the iron thiocyanate. If I rearrange this and I solve for x, which is this guy right here, okay, x is going to be equal to y, the absorbance, divided by 4,196.5, and there we go. So that's going to tell me for each of my solutions what the concentration of the complex ion is, okay? And advance. There we go. So here's the trick, guys. When you're doing the calculations for the lab, in case you guys weren't here on Friday or just want to refresh, okay, here's the point. I made for you guys the standard curve. I did this experiment. I made these solutions. I measured the absorbance. I got the graph. I found the relationship. You guys all have that available to you, and if you guys didn't get that in class, download it from the website. You'll see it. It's right there, okay? You're going to use that for your solutions that you found, okay? Here's the equilibrium, once again, that we're studying. We have Fe3 plus HSCN. Goes reversibly to my complex ion, FeSCN2+, okay, plus H+, okay? Now, here's the whole point. What I want to figure out is I want to figure out the value of K for this reaction, okay? And you're going to do this, you and your group are going to do this for 5 different trials that you performed, okay? In each of those trials, you are going to know the concentration initially of the iron ion and also HSCN. Now, where this comes from, guys, this comes from your potassium thiocyanate solution. These are the same thing. Now, why is this HSCN and this is KSCN? This has caused confusion in the past. The reason why is because this guy here is dissolved in an acid. The SCN minus ion is a weak base. If it's in the presence of H plus ions from the acid, this is going to form HSCN. So there we go. So this is the same as this concentration. The iron 3 plus ions, of course, comes from the ferric nitrate solution. Now, here's the trick. This, if you looked at the burettes, it said that the concentration of ferric nitrate was 0.002 molar or some such thing. That is not the initial concentration in the mixture. And the reason why, guys, is because when you were mixing the different chemicals in your test tube, you added iron, the ferric nitrate solution to a solution of KSCN and acid. And so the concentrations change because you're diluting it. So to figure out this initial concentration, you have to apply the dilution formula. C1 times V1 equals C2 times V2. Same thing here, guys. You have to do the same thing to figure out the initial concentration of that guy in the solution. Okay? Now, in theory, and well, not in theory, absolutely, this concentration before any reaction occurs should be 0 because these guys have to mix in a reaction in order to form the complex ion. And then here's the really tricky part. In each mixture, the H plus concentration is not 0. You might think it is, but the solvent for all the chemicals in the whole lab was HNO3, which is at a concentration of 0.5 molar. This is in every solution, okay? Now here's the thing. Nitric acid is a strong acid. It totally dissociates into H plus ions and nitrate ions. So if you have 0.5 molar HNO3 in all the solutions, that tells you that this concentration, H plus, to start with in every solution is 0.5 molar, because this totally dissociates and totally makes H plus and nitrate. So this is going to be 0.5 molar. Now, if you could figure out the concentrations of all these guys here at equilibrium, you could calculate the value of K. Here's how you're going to do that. You measured the absorbance of your different solutions. What you're going to do is you're going to use your measured absorbance, and you're going to use the standard curve. You're going to find X, which is the concentration of FeSCN2+, and that is going to be at equilibrium, once the system has established equilibrium. So if we're filling out an ice table for the problem, or for this particular mixture, we can put the equilibrium concentration down here. Let us say, for the sake of argument, that that is 0.050 molar, okay? If this is the concentration of this guy at equilibrium, and the initial concentration is 0, that tells me the change in this concentration was plus 0.050 molar, okay? And there we go. And by using stoichiometry, I can figure out the change in everything else. Then I can find the concentrations at equilibrium of the Fe3+ ion and HSCN and the H plus ion, and then I can calculate the value of K. You guys are going to do that for each trial. I strongly recommend that you completely ignore the directions on the calculations that are in the lab handout. I strongly recommend that you find the value of K for each trial like this, okay, kind of following this approach. And if you guys need to, or actually, I should say, if you guys weren't here in the third period on Friday, again, there's some guidelines on the website in the AP Chem download section that you guys need to download, print off, and follow that when you guys are writing your report. Also, get in contact with your comrades that were in class, because you will need to collaborate as a group, as a foursome, to make your final product. Okay, so, guys, that is the very end of the instructions here on the podcast. I will not be in class on Tuesday. I will be back on Wednesday. So Tuesday we'll have an assignment for you. Diligently apply yourself to that. If you guys have any questions about the Beer's Law problems, I'm going to put on the website that you guys also need to download and do. Make sure that you ask me those questions when I get back on Wednesday. With that, I hope you guys have a good rest of the weekend, and I will see you later. Goodbye.